All right, let's get started here. My name is Tony Gibbs. I'm a database specialist SA here with Amazon Web Services, and I'm here with Harshita Patel. We're going to take you guys through a deep dive best practice session here on Redshift. So thank you guys very much for coming. I know it was a last minute addition to the catalog. Before we get started, I always like to see where you are all at. How many people here are using Redshift today, day in and day out? Okay, good chunk of you. How many of you aren't using Redshift, but maybe you're starting a proof of concept, some sort of bake-off, you're considering using Redshift going forward? Okay, that's almost like the other half. How many people here don't use Redshift at all, don't really have any intention, just came here to learn a little bit more about it? Okay, a few, but not very many. This session is designed primarily for people who use Redshift. It is a 400 level session. That being said, the architecture and concepts is kind of a bit review, so this section will be really good for those of you who aren't using Redshift if you're just doing a bake-off POC or you're just wanting to learn more about it. After that, we're going to jump in deeper into the data ingestion, ELT, that sort of thing. I'm going to then hand it off to Harshita. She's going to walk you guys through workload management, cluster sizing. She's going to touch on a new feature that we recently released called Amazon Redshift Advisor. She's going to give you some extra learnings to close out with. I don't anticipate a lot of time for open Q&A. If there is, we will do that. If not, we'll do it in the hallway. There's a nice big section out there. We will answer questions for as long as you guys have them. I think last year I was kept around for almost an hour and a half. So if you guys want, we will answer as many questions as you have. So let's get started here. So Redshift really starts out life from Postgres. If you connect to Redshift, depending on the client you're using, you might even notice a connection Postgres string come back. We entirely rewrote the back end. It is entirely columnar, so the storage engine is nothing like Postgres. It's also MPP, so Redshift has the ability to scale out horizontally up to 128 compute nodes or 8.2 petabytes of storage. We added a lot of OLAP functions, linear regressions, windowing functions, approximate functions, and we recently even added geospatial support. So if you have geospatial needs, we just added over 40 functions and a new data type for geometry for that. We wrapped everything up in AWS, integration with KMS, S3, IAM, and it's the combination of all of these pieces that make Redshift what it is. We launched Redshift Valentine's Day 2013. It was originally announced at reInvent 2012. And since that time, we've continued to innovate. We typically roll out a patch every 2 weeks to Redshift. You just set a 30-minute maintenance window. We roll that out. We take care of all of the maintenance of both Redshift, the operating system underneath. It is a fully managed system. The last 18 months have been particularly exciting. We've been adding more and more features. I won't talk too much about them. There's a What's New session tomorrow that I recommend checking out. But in the last 18 months alone, we have rolled out more than 200 new features and enhancements to Redshift. So Redshift is an MPP, share nothing, columnar architecture. I'm going to start up at that top green box there, the SQL client and BI tools. That's what you use, whatever tool you happen to like, to connect to Redshift. You connect to Redshift with either JDBC or ODBC drivers that AWS supplies, or if you're wanting to use, say, maybe .NET or Python, R, Ruby, some other development language or some other tool that needs maybe a .NET driver, you can connect with the open source Postgres driver as well. So Redshift still works with the latest open source Postgres drivers. What you connect to is that one blue box up at the top there that says leader node. You connect to that. It's a query coordinator. It holds a lot of metadata. It does final steps in the query processing, such as aggregations or final aggregations, order bys, that sort of thing. Behind the leader node are between 2 and 128 compute nodes. In this example, I have 3. When data is stored in Redshift, in theory, it should be stored evenly across all of those nodes, and every single node in the cluster executes the query against the data that resides on it. It then passes those results up to the leader node, which stitches things together and gives you back the answer. Underneath the compute nodes here, I have S3. Redshift, you typically are loading data in to Redshift through it, or you can unload data out of Redshift with that. Backups, restores also work through S3. Those are completely seamless and taken care of for you. Backups just automatically happen in the background. A restore is just a few clicks of a button, and you can launch an additional cluster off of a backup. Then last year, or about 2 years ago, or a little over 2 years ago, we launched something we call Spectrum. Spectrum is a layer of compute that sits between your compute nodes and S3, and it's provisioned dynamically at query time. And what it does is it exposes your data, probably, hopefully in a data lake, and that data might be, say, in Parquet or ORC, CSV even, JSON, et cetera. And it allows you to expose that raw data on S3 into Redshift as an external table. You can then query that external table with the same SQL syntax you use for any other table in Redshift, and you can even join the data in S3 to local tables stored in Redshift. But the Redshift architecture is evolving. All of the same stuff that I just talked about up there in the top left, but we yesterday announced Redshift Managed Storage. This effectively separates storage and compute and allows you to provision each of them independently. So what you can do is you can purchase the number of compute nodes you want. Each compute node can scale its storage up to 64 terabytes, and it's completely taken care of for you. It's a mixture of SSDs and S3, and Redshift just moves the blocks. It's at the block level, back and forth between whatever makes sense based on your query patterns. This is how Redshift can now scale over 8 petabytes of raw storage. We also announced yesterday Aqua in the keynote. And what Aqua essentially is it's AWS designed analytics processors that are close to that storage. They are in the Redshift managed storage layer, and they take care of things like encryption, decompression, filtering, and being able to do some aggregates. So it's hardware accelerated chips that are able to speed up those certain operations and also limit the amount of data movement across the network with this Amazon Redshift managed storage. So I'll talk, we previously had 2 compute node types, DC2, which was our dense compute. So those were SSD-backed heavy amounts of compute. And then we had our dense storage node type, which is magnetic disks. So previously, we just had those 2 choices, and customers had to pick between those depending on their storage or compute nodes. We now have this new RA3 instance, and that's what kind of changes things a bit, because now what you can do is you can pick the number you want and then just let Redshift, or you save whatever data you need and let Redshift scale that out automatically behind the scenes. We launched yesterday, and it is GA, the RA3 16XL. The RA3 4XL, which is a smaller version of it, will be coming soon, sometime next year. So let's jump into columnar storage. This is a pretty basic concept, but I'll cover it because there are some people who may not know what it is. In a data warehouse like Redshift, where you're typically running analytics queries, you're usually only selecting a subset of the columns in the table, and you're wanting to perform operations across many millions of records, or in certain cases, even billions of records. A columnar architecture helps us reduce I/O and achieve better performance results. Just to illustrate how this works, say we have a very simple table, call it deep dive. I have just a handful of sample rows there on the right, and I have this very simple SQL query where I'm just selecting the minimum date out of this table. If I was in a row-based database, we could say Postgres, I would need to scan through every record in this table to find this answer, assuming I don't have any help from an index. In a columnar data warehouse like Redshift, I can just read the data through that date column and get the answer back. So that's how one of the ways that Redshift is able to achieve the performance that it can is with this columnar architecture. The next piece is compression. Redshift, we typically want to compress data in Redshift, and Redshift will do its best to automatically apply compression. The reason we do this is, one, it allows you to store more data in your cluster, which reduces the cost for you, which is really important. The second thing is in almost every case, it also increases the performance, and you actually get better query performance out of it because you're reducing the amount of I/O you need to do. Just as an example, the same deep dive table, the same sample set of rows. There are one of 13 different encoding or compression types. I'll use the two terms a little interchangeably. And we have these blocks here up for that table. So if I were to modify the DDL here for this table, and you can see the encode statements up there in red, you can see that each column shrunk independently from one another. So that means that the compression is applied column by column rather than across the whole table. And we're able to do that because it's a columnar storage engine. So earlier this, or actually only a couple months ago, we released a new compression type that we call AZ64. It is an encoding type that we built in-house. We set out with a couple of goals here. The main one was we wanted to increase compression ratio, but we also wanted to increase the performance as well. So we set out some pretty lofty goals when we went about building this. You can see down below here, these are some of the performance numbers that we've achieved over two of the most common compression types we used in Redshift, which was LZO and Z-standard. That's what most customers were using across the board. And so this new AZ64 is able to beat both of them, especially in the performance side, and it's able to match Z-standard for compression footprint. It works for all of the integer type data types, so integers, big ints, small ints, dates, timestamps, etc. The nice thing about now that we have this new encoding type is that I can pretty much give you guys a recommendation now that says if you have one of those data types, you pretty much just almost always want to use this encoding type. So it's a really nice across-the-board recommendation that I can give. For varchars and chars today, you'll probably want to stick with either LZO or Z-standard. So the encoding types they're pretty set now on what you'll use. If you do want to find the absolute smallest amount of space or squeeze that table into the least amount of storage space, the Analyze compression utility, it's built into Redshift, will analyze your table. It picks up a set of the table and compresses it with every encoding type we have and gives you back the smallest. So I say smallest, not most performant. So it does not factor in any performance, it just gives you the smallest. That little SQL snippet there, that snippet will, if you're looking for what encoding types you currently have on a table, that's how you can figure that out. So let's introduce you to blocks. Blocks in Redshift are immutable. So it means we never go back, we never change an existing block. They're also very large. They're 1 meg. They're encoded with one of 13 encodings. I have seen sometimes blocks even containing millions of values. Usually when I take a look at a block, there's usually about 300,000 or so records in a single block, but in certain cases, if you get really good compression, it can be in the millions. So let's introduce you to zone maps. Zone maps are an in-memory data structure in Redshift. What they essentially are is the minimum and maximum values for each block. Redshift automatically keeps track of these. You don't have to do anything. It's more just so that you're aware of it and how Redshift works. We use these zone maps to filter out which blocks we read off disk at query time. So that's the purpose of them. The next piece of terminology is data sorting. Data sorting is meant to optimize the zone maps. That is like what 90% of customers will use data sorting for. So you want to basically make the zone maps more effective and reduce I/O further. It's in most cases in Redshift, it will be on some sort of temporal column, usually a timestamp or a date, something that you're frequently filtering on. This is data warehousing, so there's almost always a timestamp in your fact table. So a simple example of how data sorting works, the same deep dive table, the same 4 rows there. If I were to manually modify the DDL for this table and apply this sort key, which would be sorting the table first by the date, then by the location, we would end up sorting it. First, you can see by the date. Then we have a tie, so then it goes over to the location, which is this JFK, and then SFO. So that's how data sorting works in Redshift. Tying all of these concepts together in data sorting and blocks and zone maps. Say we have these 4 blocks. I have the zone maps printed out beside them, the minimum and maximum values. We have this really simple SQL query. I'm just counting the number of records on a particular date. what Redshift will do is it checks the zone maps and it knows that it doesn't need to read data out of that one block, and we've reduced I/O. Now, if I were to take these same 4 blocks and I was to sort the data in them, I would might end up with some zone maps that look like that. You can see they go in sequential order now. So now, if I were to run this query, I know that my data for doing this count would only fall in that one block, and now I've reduced I/O further. So this is the main purpose of a sort key in Redshift. So just kind of a bit of summarization on sort key best practices. It's usually on a temporal value. If you do frequently filter on something else, sometimes I've seen customers, they have like a location ID or something like that, or an office ID, and it's a really low cardinality value. The lower cardinality values go first. So that might be a case where you would place that column ahead of the timestamp. If you ever have a high cardinality value, maybe you have a timestamp and it goes all the way down to seconds, and it's really high cardinality because of that, it does not make sense to add additional columns to your sort key after that. I also usually recommend keeping the number of columns in a sort key usually somewhere between 1 and 3. Once it starts reaching 4, 5, 6, it's all diminishing returns at that point, and it means that the sorting takes longer. We have a couple of scripts here on YouTube if you have an established workload that can give some recommendations as well for sort keys. So I'm going to talk about a little bit about materializing columns now that you guys understand zone maps. I usually see this one come about with migrations from existing legacy systems. In a lot of legacy systems that are especially coming from row-based databases, we typically would normalize our tables very heavily. Redshift being columnar and having these zone maps work the way they do, it actually makes a lot of sense to denormalize quite a bit. So in this middle example here, or in the middle of the slide here, where I have these 2 SQL queries, the first one, I have this date dimension table, and I'm joining to this date dimension table, which probably only has 10,000 or so records in it. And what's happening is I'm running the filter on that dimension table, and then I'm taking the values, and I'm probably doing a hash join back to my fact table. And I'm not able to leverage the zone maps as effectively. In that second query there, what I've done is I've taken my dimension table and I've materialized the values into my fact table, and now Redshift's able to fully leverage the zone maps and reduce I/O. So that is one recommendation that a lot of times when I'm helping customers with migrations, I recommend making. The second example applies pretty much to every database. It's pretty much if you have, you're doing calculations on a column. In this case, I'm extracting out the epoch out of that column. In that case like that, if you were to instead just simply materialize that and write it out into its own column, that will also greatly improve performance. So just a couple kind of things, especially if you're moving from legacy systems. So this next concept, really important in Redshift, slices. It's how we get parallelism within each one of our compute nodes. The easiest way to think about them is they're virtual compute nodes. So every one of our compute nodes divvied up into either 2 or 16, depending on the size of it, virtual compute nodes that we call slices. The data, when you write data out to Redshift, it is essentially spread out across all of these slices, kind of sharded out. And that's how we're able to kind of spread all of that data and do everything in parallel. So I'll talk a little bit now about how we actually get the data spread across all the slices. We have 4 ways of doing that. The first is distribution style key. What that does is if you take one of the columns, you put a distribution key on one of the columns, and for every row in that table for that column, what we do is we take the value, we hash it, we then run a modulo by the number of slices in the cluster, and that's where that entire row goes in the cluster. And I have an example for that in the next slide. Dist-style all is kind of a special case one. What it essentially is it's make a complete copy of the table on every single node in the cluster. It's typically used for really small tables, dimension tables. We define that as small as being 3 million records or less. The last one, or the next one, is distile even. And what even is it's kind of like saying Redshift, I'm not really sure what to do. Just round robin or just spread the data evenly across the cluster for me. And that's exactly what it does. Distile auto, what it does today is it combines even and all together. So if you have a small table, it's going to start out life with distile all. As the table grows and it reaches a certain threshold, it automatically converts into an even table. So that's what distile auto does. So just to illustrate these, say we have same deep dive table, and we have some rows. And down here underneath here, I have 2 compute nodes, each with 2 slices. And I'm going to distribute those 4 records with distile even. Like I mentioned before, it's just going to round robin the data, one slice to the next. Really simple how it works. So let's move on to distile key. I'm going to pick the location column. So these are these values, SFO, JFK, SFO, JFK. And what this is going to do is we're first going to pick up that SFO, and maybe it hashes out to there. And JFK, maybe it hashes out there. SFO is going to go back to that slice 0, and JFK is going to go to that same slice 1, because they're going to go to the same place. This is an example of a poor distribution key. And the reason why is if I were to execute a query against this cluster, it would only execute on node 1, and node 2 would do none of the work. So we can do better. I'm going to pick the audience ID here, which looks a little bit like a primary key. And if I were to now distribute by this, 1 might go to slice 1, 2 might go to slice 2, 3 goes to slice 0, and 4 over there on slice 3. I baked the example, obviously, so it works perfect. But if you have millions of records or billions or whatever it is, a very large number, and it's a high cardinality value like that, something like a primary key, the data will be mostly evenly spread across the cluster. So what about distile all? Like I mentioned, we write every row to both nodes in the cluster in this case. So in this case, we write it out to the first slice. And that's how distile all works. So just summarizing this, dist key is typically used for joins. What we want to do is if we have 2 large tables and the on clause in your SQL statement, whatever those 2 columns are, those are the ones we would like to distribute both tables on. That will do what we call co-locate the data onto the same slice, and that makes the join really fast. So we want these co-located joins. The other common use case that customers use for using dist keys, and this comes up a lot in ETL, is if you have 2 tables and you're inserting data and selecting it from one table into another, if both those tables have the same distribution key, that operation is much faster. Distile all, primarily used again, also for joins, but with small tables. There's also a little bit of, I'm not sure what to call it, nuance, I guess, in that in certain cases, if the table is small, it can actually also reduce your disk usage as well with small tables. So if you have these small tables, which we define usually as being 3 million rows or less, it makes sense for them to be distile all. Even, like I said, it just evenly spreads the data across the cluster. And auto, which is the default in Redshift, is just a combination of even and all. So this summary slide is pretty much everything that I've just been saying. I mostly stuck it in here because these slides are all going to end up online, and it repeats a lot of what I just said. One extra point that I put in here is this distribution of keys on temporal columns. It's something I pretty much never recommend, even if it doesn't cause skew in your cluster and all the data is evenly spread. And that's because, say, like you pick something like a date, for example. A date being, every single day. And we'll say maybe you have 7 years of data and it is spread evenly across the cluster. In a case like that, though, you might run a SQL query and your predicate says, hey, just run on just this one day. Well, what's going to happen is now only a single slice in your cluster is going to execute against that day. And it's kind of this form of in-flight query skew that's happening at runtime. So pretty much in all cases, I always recommend steering you away from distributing by anything really temporal. Other than that, the rest of this is just review. So let's move into data ingestion. So redundancy. Redshift has these, it's a two-phase commit, which I'll talk about on the next slide. But when a commit happens, the global commit in Redshift, all of the data is at least written to 2 places in the cluster. And we do this for redundancy reasons and safety. We also back all of the data up to S3 asynchronously. So that just happens automatically. Today it's every 5 gigs of data or 8 hours, whichever happens first. The important piece, or the reason to understand that these multiple copies of data is that there's an exception to that, and that's temporary tables. Temporary tables don't only write data out once. There's no second copies of them. And that has an important impact on performance. They happen to be around twice as fast to write to as permanent tables. So let's talk about transactions. I mentioned that transactions, there's a 2-phase commit. There's what we call a local and a global commit. And in Redshift, because it is an ACID compliant, it's fully transactional database, because it's MPP, we happen to only implement isolation level serializable. So you can ask for repeatable reads or whatever it is, read committed, but you'll always get serializable isolation level. It'll actually say, yeah, okay, I give you that, but you are still in isolation level serializable. The one thing to be aware of with this then is that commits are a bit expensive in Redshift. It's not an OLTP database, it's a data warehouse. Sometimes customers don't realize that DDL is transactionable in Redshift. So if you have workflows where you're modifying a whole bunch of tables, maybe you're creating a table, renaming a table, and swapping things around, each one of those, if you don't explicitly wrap the workflow in a transaction, is implicitly creating transactions. So it's a best practice in Redshift if you have a workflow, particularly in ETL, to wrap everything up in a transaction. So let's talk about how you get data in Redshift. There's a couple different ways. The primary way is with the copy statement. That is the primary way everyone loads data. In this particular example, I have an RA316XL, which isn't technically a valid cluster config, but we'll just go with it. And I have these 16 slices up there, which are represented. And I have this one file on S3. And I execute the copy statement against it. What's going to happen is Redshift is going to pull that one file up, and then it's going to distribute it and spread it out across the cluster. And that's not really all that efficient. If instead what we did was we broke that single file up into 16 pieces, now what's going to happen is all 16 slices in this cluster are going to reach out to S3 and pull up that data. This will run 16 times faster than the previous example. So ideally, you want to have as many files as you have slices in your cluster, or a multiple of that. So if I had 32 files that were all the same size, that would also work just as well. Our rule of thumb, or rough recommendation, is that files in S3 should be somewhere between 1 meg, 1 gig after compression. So usually most customers will compress the data with gzip. These are just a handful of recommendations that I've put together over the years, just where I've seen customers run into things. Keep your files simple. I always recommend delimited files. They could be tab delimited, they could be comma, whatever it happens to be, pipe. Keep things simple though. Don't pick crazy UTF-8 characters, unprintable characters. It makes life painful. Pick a simple character for null. You can always wrap strings in double quotes. There's escaping, all of that kind of stuff, and all of that works in Redshift. If you want to know how many slices your cluster has, that simple query there will return you back the number of slices. Another way to ingest data into Redshift is through Spectrum. So I mentioned Spectrum earlier, how it's typically used for external tables. Well, you can also create an external table, and you can do an insert out of that external table into a local table as well. And this is really nice if you want to be aggregating data off of S3 on your ingestion step, or maybe you want to only select a subset of the columns, or you want to do some row filtering or that sort of thing, or you happen to have data in a format that the copy statement doesn't support. So let's talk about how Redshift is designed around big data. So small writes, which are typically done in OLTP, they are as expensive in Redshift, typically as ingesting hundreds of thousands, or even in some cases, depending on the size of your cluster, millions of records. Redshift's not designed for small updates, inserts, that sort of thing. And the reason why is because of those really large 1 meg immutable blocks. So if you want to, for example, do an update in Redshift, what we end up doing is you're updating maybe just a single record. We have to find that record first, which isn't a big deal. Then we have to go and figure out where all the blocks are across. We have to read all the values out of those. We mark that record for deletion, and we add it to the end of the table. It's an expensive operation. It technically works, but it's not something you want to typically do repeatedly. If you need to do it once in a while, it's totally fine. Deletes in Redshift are actually quite fast. They just simply mark records for deletion, and it's a very fast operation. We now have auto vacuum for deletes that will automatically take care of deleted records. So if you are deleting a lot of records, the auto vacuum process will come along and clean that up. We have some other best practices around vacuum, which I'll cover in the end of this section. So this is a very frequent ask that I get customers that ask me on this one, which is deduplication or UPSERTs. How do you do that? So I have the same 4 records in this deep dive table that I've been going through for this whole session, and I have this CSV file here. We'll say the CSV file is sitting on S3 somewhere, and I want to basically update those 2 records, and I want to add 2 records to the end of this table. How do you do that with a copy statement, which is append only? The workflow is that I'm going to load the data into a staging table, that CSV, with a copy statement. I'm then going to delete the duplicate records out of my production table, and then I'm going to insert everything out of this staging table into my production table. So that's the steps that I'm going to go through. Now, the sequel for it, I'm going to start a transaction. And the reason I'm going to do this is, remember I was talking about wrapping workflows in a transaction, reduce the number of transactions. It's going to start with a begin statement here. I'm going to create a temporary table, because temporary tables, they're twice as fast, so that makes sense for a staging table. I'm actually going to also use this like keyword here. And the reason I'm going to use that is it's going to copy over the distribution key from my other table, from my prod table. It's also going to copy over compression settings as well, which is nice. So the staging table now has the same distribution key as the prod table. I'm going to then copy the data into my staging table. I'm going to delete the data on that. I'm going to join on that AID there. I'm going to delete those 2 records out. Then I'm going to insert all of the records over. Then I'm going to drop the staging table. I'm going to commit the transaction. So this workflow, or variations of it, are the optimal way to do this UPSERT dedupe logic. So I'm going to just walk through, this is a really, again, summarization. Staging tables, try to use temporary tables if you can. If you can't, there's a backup no option. All it does is it disables the asynchronous sync to S3, so you can disable that. Like I mentioned, keep the same distribution keys. There's the copying over with the like statement, or using that like keyword will copy over distribution keys and compression and such. There's also it's kind of, I wouldn't say it's special, it's in the documentation. It's called alter table append. If you are moving or need to move very large volumes of records, like I mean hundreds of millions or maybe even billions of records in your workflow, instead of doing an insert into with a select, you can use alter table append. It's a DDL command, and what it does is it takes the blocks in the staging table and it appends it onto the columns in your prod table. So it's all metadata rewrite, and it allows you to essentially move data almost instantly. So it's a really useful command if you're doing that operations like that on very large sets of data. So I'm going to talk to you guys a little bit about vacuum. Vacuum does 2 things in Redshift. Vacuum removes the deleted records, and it also globally sorts the table. So there's 2 tasks that it does. Auto vacuum delete has been out for some time now, so deleted records, they should just automatically be taken care of by vacuum. There is also what we call auto table sort. It's not quite the same as vacuum, but it also runs in the background. And what it does is it looks at the hot portions of the table that you're typically querying, and if those sections aren't sorted, it sorts them. So it's kind of a little bit like auto vacuum sort, but in a light way. Then we have this other command. If you do need to do a manual vacuum and you're able to do it maybe in the middle of the night or some off hours, we have what's called vacuum boost. And what vacuum boost does is the boost part of vacuum is it's significantly faster than just running vacuum without the boost command. But with boost, you won't really be able to do much else on the cluster running other queries and such. So if you do need to manually vacuum, just consider that extra keyword there and tacking that into your workflow. The last step here, analyze. Analyze is largely taken care of entirely for you by auto analyze. In certain ETL cases, it can make sense to analyze just a specific column if you're frequently filtering on that. There's a utility on GitHub you can also use there that manually vacuums and analyzes all of the tables in the cluster. I think it's pretty redundant now that we have this auto vacuum, auto analyze, and auto table sort. And I am now going to hand it off to Harshita.
Hello all. Now we'll dive into workload management, WLM. When you have an environment with mixed workload, a workload loading the data, performing ETL and ELT, another set of workload coexisting, your dashboard and reporting queries being run by your MicroStrategy and Tableau users, and in the mix you have your ad hoc workload being run by your data science team or your data analyst team. The purpose of workload management is to allow the resource separation to these different workloads. So say during a given business day, you want to give priority to your dashboard queries and your reporting queries and throttle down your ELT workload, which is a low priority. This is the purpose of workload management. In Redshift, what we have is called queues. When you execute a query in Redshift, that query will execute in a queue. Based on the user or the user group you belong to, or by setting a query group in the session that you're executing, that is what determines which queue that query is going to execute in. A queue is divided into slots. Each of the slot gets a percentage of memory. The number of slots determine how many concurrent queries you can run or execute in that queue. We have this concept called a short query acceleration. You can either enable or disable it. I would recommend you to enable short query acceleration. The way this feature works, when the queries start queuing, Redshift will detect that this particular queued query is going to execute in few seconds. It would tag it as a short query. So instead of allowing the short queries to wait in the queue, it's going to route those short queries to a special queue, which is the short query queue. So your short queries can continue to run even if your system is fully loaded. Concurrency scaling is a significant feature which was released on March 27th of this year. This allows you to handle your spiky workload. So let's take a look at how concurrency scaling works. You're submitting, we'll use the dashboard query as an example as that workload. We are submitting queries to Redshift. As soon as Redshift detects that queuing is occurring, it's going to take, I'm going to build out the slides a little bit here. Redshift is going to take an automatic snapshot, an incremental automatic snapshot, which is very quick, push it down to S3. It's going to spin up a transient cluster, which is a secondary cluster, and the queued queries are going to route to the secondary cluster. So this is shifting the workload from your main cluster to a secondary transient cluster. As in when you're submitting more and more queries, it can spin up additional concurrent clusters. So from the point of detecting the queries are being queued, spinning up a transient cluster, routing the queries, and when the depth of the queue goes down, those transient clusters are relinquished. All of these is fully managed by you, by the service. From your perspective, you choose whether you want to turn on or off concurrency scaling. And when you turn on concurrency scaling, you can choose the option of how many transient clusters do you want Redshift to spin up. You can choose from 1 to 10, 10 being it's a soft limit, it's not a hard limit. With every 24-hour use of your main cluster, you get 1 hour of concurrency scaling capacity for free. So say, for example, you have your cluster up and running 30 in a month for 30 days. You can accrue total of 30 hours in a month, which is the free capacity that you can use. What we believe is if 97% of the customers, if they turn on concurrency scaling, they will be able to leverage this particular feature completely for free. So leverage the free capacity for your spiky workloads. Let's marry the concepts that we talked about with WLM using this scenario. This is a very common scenario we have seen with customers, where there is a need to continuously ingest the data throughout the day. During the business hours, there are report and dashboard queries running, but there are also peak hours within the day where there will be a spiky workload. Say, in the morning or in the afternoon hours, you'll see a peak that requires there is a peak in terms of queries being submitted for the dashboard workload. And the nighttime or the nightly batch is where your heavy ingestion or ETL workload is running. So let's map out for this use case, how are we going to configure WLM? So we'll start off by creating different queues. The font size is very small for this, but always ensure to turn on short query acceleration to allow your short queries to continue to run even though your cluster is fully loaded. We'll add an ingestion queue. To this queue, we are going to allocate 2 concurrent slots, 2 slots. That means 2 concurrent queries can run, and provide it 20% of memory. So each of the query is going to get 10% of the memory. To this, we are going to add a queue for dashboard. To this, we are going to increase the concurrency, or how many concurrent queries can run. We'll put the number 10 and provide the memory allocation of 50. So each of the query is going to get 5% of the memory. Say, for example, the dashboard queries are typically expected to run less than 2 minutes. You can also set query timeout for this. And because this is a spiky workload, we are going to turn on concurrency scaling for Redshift to handle it for you when you see a sudden spike in the workload. And finally, the default queue, which is the catch-all queue for your ad hoc workload. The ad hoc queries are data intensive. We'll set it to concurrency of 3 and provide it a memory of 30%. So each of the queries is going to get 10% of the memory. We also have a special queue, super user queue, which is not visible on the console. If a person is an admin, they can set this query group in the session. And when they submit the query, those queries will be routed to the super user queue. The purpose of the super user queue is to run administrative tasks. Say you want to drop a table or cancel a query. I would recommend not to use the super user queue for long-running queries. Dynamic attributes of workload management. What we looked was a configuration during a given day. There are certain attributes in WLM. For example, the number of query slots, the percentage of memory, whether we want to turn on concurrency scaling or off. Those are all dynamic in nature. That means with a simple API call, you can make the changes. It does not require a cluster restart. Let's take a look at exactly the same example that we started off. But we want to toggle for a nightly window where we want to give higher priority to the ingestion workload. And we want to throttle down the dashboard and the ad hoc workload. So for the ingestion queue, we are going to set the concurrency to 5 and percentage of memory allocation to 80. So we are shifting the resources more to the ingestion workload, which is a higher priority during a nightly batch. And we are going to throttle down the resources, the number of concurrency and the memory for the dashboard and the ad hoc queue. What we talked about is manual WLM, automatic WLM. The goal of automatic WLM is the same, to allow you to prioritize your workload. But the main objective and purpose of auto WLM is to simplify the configuration of WLM, where Redshift will automatically manage the memory allocation and the number of concurrent queries that are going to run. So this is a screenshot of the setup, default setup of auto WLM. where you will see both the memory and concurrency on the main is set to auto. You're not configuring the percentage or providing the slots. Redshift is automatically going to manage the memory as well as the concurrency. You can choose to enable the option of turning on concurrency scaling or disable it. In every data warehousing environment, you will find some queries, poorly written queries, which can be very resource intensive. A commonly asked question is, how do we detect poorly written queries? And on detection, we want to automatically terminate it. So this brings us to query monitoring rule. This complements workload management. With QMR, you can set up rules to detect those poorly written queries. Say, for example, there is a Cartesian join or a query returning billions of records to the desktop. You can automatically, when it's detected, automatically take an action to abort it or terminate it. The second common use case for QMR that we recommend the customer is to log your long-running queries. What this provides you is you can go and review your long-running queries, look at the profile of the query, and make adjustments to make them performant. Here is one simple example of how you can set QMR. You can stitch the rules together. But just wanted to highlight this. This is a return row count of more than 100 million records, a typical use case when somebody's trying to extract the data from Redshift. When you extract the data from Redshift, say 100 million records, it's going to go through the leader node. Versus if you change this query to use an unload command, with unload, you can push the data to S3, and you are able to leverage the parallelism of compute nodes and the slices to work in parallel, and that will dramatically be faster. So to summarize all the best practices, as a key takeaway, if you forget what we talked about in this session with WLM, consider using AutoWLM. If you are using the old default queue, please switch it to use AutoWLM. If your workload is very predictable, and if you have a need to toggle your WLM between your business hours and night or nightly batch, use manual WLM. I would recommend you to start with 3 queues and have the total number of concurrency across the slots to 15 for query throughput. So this brings us to cluster sizing. A common question asked is, how do you right-size a Redshift cluster, either for a POC or for a new workload? So we start off with estimating the uncompressed data set size. When that data is ingested into Redshift, it provides 3x to 4x compression. To be conservative, we'll assume 3x compression. On top of it, keep 30 to 40% of disk space or additional capacity. Please ensure that when you have your cluster, if you're using your Redshift cluster, the percentage of disk utilization is below the 80% watermark. Based on the workload, based on your performance requirement, you can either choose to have dense compute or dense storage, and now RA3 cluster. So with this recipe, let's map it out. If we start with 20 terabyte uncompressed data set with 3x compression, you get 6.67 terabyte. That's the size that you start with. And depending upon the performance requirement, you can either use 4 DC28XL or 5 DS2 extra large cluster, and now 2 RA3 instance. So with RA3, you get the elasticity of the compute and the storage. Say you started off with one of the compute node based on the recommendation. When you ingested the data, maybe you get more compression. If you wanted to change the number of compute nodes, use resize. If you started off with DS2 and DS2 was not meeting your performance requirement, and you wanted to switch to RA3 or DC2, again, you can use a resize the cluster. In Redshift, there are 2 types of resizes. One is the classic resize, which is the old resize, where Redshift provisions a new cluster, transfers the data from old to the new. And with classic resize, you can choose to enable or disable the encryption on the cluster. An elastic resize is the compute nodes are added or removed from an existing cluster. So let's map this out of how classic resize works. We'll start off with DC28XL, 3 compute nodes. Each of the compute node has 16 slices. when you instantiate a classic resize, an entirely new cluster is spun up. The primary cluster goes into read-only. The data is then transferred from the old to the new. That data is redistributed across the compute node and across the slices. And then the DNS is changed, and it's pointing to the new compute node. So with classic resize, we started off with 3 compute node, 48 slices, and we ended up resizing up to 4 DC2 8XL, so total number of slices is 64. Let's map the exact same example, but using elastic resize. So with elastic resize, we want to add storage. So when you instantiate elastic resize, a new node is added to the existing cluster, an incremental snapshot is taken, pushed down to S3, and then the metadata is moved, or the slices are moved to the new compute node. And this duration is of 4 minutes. If you have in-flight queries, they will be parked. If you have a query in a transaction for write, it's going to roll back. Once this stage is completed, the data gets hydrated from S3 onto the new compute node. Redshift is aware of the frequently accessed blocks, termed as hot blocks. Those are the blocks which are going to get hydrated first. And during this entire hydration, the cluster is available for read and write. So with elastic resize, there are limits and ranges that you can resize up or down the cluster. So if you start with a cluster initial configuration, either you can go to 2x or half x. If you're using the smaller instance family, which has fewer slices, if you started off with 4 compute node, you can go to 8 or down or half size, which is 2. If you're using the larger instance family, which has more slices, you have more options. Say you started off with 4 compute nodes, you can go all the way to 8 and half size to 2, but every intermediate point in between. So you can go from 4, 5, 6, 7, 8, or from 4 down to 3 and 2. So when do you use elastic resize versus classic resize? One common use case of elastic resize is for a known heavy workload. So you want to do, you might have a weekly refresh, or month-end reporting, or quarterly reporting, which are high-demanding workload. Customers will resize up the cluster to shrink the duration of those heavy workload. And when the workload is completed, they will resize down the cluster. With Amazon Redshift, it was just announced last week, Redshift Scheduler. So now you also have the ability to schedule your elastic resize using that scheduler on a cadence. You choose to use classic resize if you want to change the instance family. And the primary distinction between both of these resizes is the duration and the amount of time it takes. Elastic resize, 4 minutes of park connection, and classic resize, it's based on the amount of data that it needs to transfer. So consider classic resize as an overnight operation. Let's put all this together. I would recommend for your production cluster, use 2 or more compute nodes because you want to have the redundancy of an additional compute node and the mirrored data copy for fault tolerance. Keep 20% of free disk space. If you're using DS2, consider migration to RA3 because you will get more price performance. Now with Redshift, you can do cross-instance restore. So if you have a snapshot from DS2, you can restore that snapshot directly to DC2 or RA3 or any other instance type. If you're using DC1, I would recommend you please upgrade to DC2 because DC2 provides you twice the performance and the upgrade is free of cost. This brings us to one of my favorite features in Redshift, Advisor, Amazon Redshift Advisor. We talked about a lot of best practices. We talked about table design, copy, best practices. But what if all these best practices are provided to you or recommended to you on a daily basis based on your workload and your cluster configuration? This is what Redshift Advisor does for you. This is available on the console on the left-hand side. It scans through the metadata every day with the lens of best practices, makes observations and recommendations which are actionable and of high impact. So to list out a few of the recommendations, not all of them are here. To list out a few of the recommendations, Tony mentioned about the copy command to make it performant, split your file, compress your file so all the compute node and slices can work together, as well as skip the comp update step, which does compression when you're doing copy. So these recommendations are captured and available to you on the console for your workload. If you're using manual WLM, if your queues are not completely being utilized, it provides you the recommendation that the queues are not utilized, so you can make a shift. It also provides you a query which would give you insight into how your WLM queue setup is performing. If you're using Redshift, and if you're not utilizing the cluster, it would make that observation and recommend reduce the size or take a snapshot and delete the cluster for cost savings. The same thing with enable short query acceleration. And now with Redshift, you can alter distribution key using an alter table statement. Redshift Advisor looks through your query patterns, makes a recommendation on a distribution key, which is going to provide you optimal query performance. It will provide you an alter statement, and you can copy and execute that alter statement. If you're using Redshift, if you have access to Redshift Advisor, if you don't see any recommendation, you get a thumbs up and 5-star. That means you're implementing all the best practices. To leave you off with additional resources, here is a Redshift GitHub toolbox. This has been developed internally by us, and this is available to you for use. And specifically, the admin scripts, the admin views are the one that we internally use and a lot of our customers use to gain insight into the Redshift queries and how the workload is performing. Here are the list of the blogs to leave you with. The first blog, Advanced Table Design Playbook. This blog is an in-depth blog which walks you through, it's an excellent blog, which will walk you through advanced concepts and topics. The top performance tuning techniques for Redshift, a lot of the best practices we have covered today, but because this is 1 hour, there are additional tips and tricks that you will find in this blog. And if you're using Redshift Spectrum for your workload, this last blog will provide you best practices. It's a great blog, which will give you insight into if you're using Spectrum, what is right, how to optimize your query, as well as how you calculate the cost of Spectrum queries. If you're interested in taking certification and training or build your toolkit, we also have this new database specialty beta exam available that you can take. I really want to thank you all for taking the time and joining us today. Hope you all are enjoying reInvent.
Excellent.
Thank you.
Thank you, guys. I'm not sure if there's any microphones or not, but if there are, I can do some Q&A. I think we have 2 minutes left, or we can just go out in the hall and do it out there. That works as well, because I don't see any microphones set up for this. So we'll just do Q&A in the hall then and clear out so they can get the next session in here. Thank you.
Thank you.